in this video we are going to discuss about Unit 4 in optical communication. So Unit 4 is nothing but optical receiver, measurements and coupling. So let us see the syllabus of Unit. So this is the syllabus of Unit 4 optical receiver, measurements and coupling. So we can split this syllabus into three parts. So the first part which deals with the optical receiver and the associated circuit. The second part of your fourth unit which deals with the measurements. And the third part is nothing but power launching technology. And this is about the syllabus of Unit 4. So today in this session we are going to discuss about the fundamental receiver operation of optical communication. So here it is. And this is the block diagram which will give you the differences between the general communication system and the optical fiber communication system. So we know that basic difference between these two. So in this case of general communication system, the transmission medium, it may be in copper wire or it may be an air medium. But in the case of optical fiber communication system, the medium is nothing but optical fiber cable. So since we are going to send the data by means of light signal, then it is necessary to have optical source at the transmitter and at the same time optical detector at the receiver side. So the purpose of this optical source is that to convert this original electrical signal into the light signal. So light signal we can call it as optical signal. And then we can just connect that optical fiber cable as a medium, and the other end of the optical fiber cable that can be connected to the optical detector. Here the purpose of this optical detector is that to convert this light signal into the original electrical signal. So this is the difference between the general communication system and optical communication system. So next is nothing fundamental receiver operation. That is why we go for this receiver operation. That is what is it? The basic function of this optical receiver is nothing but it is to detect the weak signal and also to amplify the signal. That is the main purpose of this fundamental receiver operation. So what are the major requirements of your fiber optic communication? Which are nothing but you should have the wide dynamic range, excellent receiver sensitivity, and at the same time you should have the fast acquisition time, and at the same time you should have the wide range of bit rates. So these are all the basic requirements or can put as major requirements of any receiver circuit. Now we can just look into this block diagram. So which consists of optical transmitter in your left hand side and the other side there is an optical receiver. So in between this optical transmitter and receiver, the medium called optical fiber, what we discussed so far. So this is the actual input signal that can be given to the encoder, or we can call it a signal shaping circuit. And that will be connected to the driver circuit next to that optical source. So here either we will be using that LED or laser diode as an optical source. And output of this LED that can be given to the optical fiber, the other end of the optical fiber that can be connected to the photodetector. And there also there are different types of photodetectors, and in most of the applications we'll be using the pin photodiode or avalanche photodiode based upon the application. And output of that photodetector is given to the amplifier. So this amplifier we can call it as pre-amplifier circuit. The output of this amplifier it is given to the decoder, or we can call it as demodulator. Finally we'll be receiving that signal, the original signal at the destination point, and which is same as that of the actual input signal. So this is about the fundamental receiver operation. So the next diagram which shows the basic sections of optical receiver. So here this design of this optical receiver is much more complicated than that of an optical transmitter. Why? Because this receiver must first detect the weak signal and then distorted signals, and then it should make the decisions on what type of data was sent based on the amplified version of this distorted signal. So when this optical data are incident on the avalanche photodiode or twin photodiode, so higher current pulses flows through the circuit. So that current we can call it as photocurrent. So this photocurrent is amplified by means of this pre-amplified circuit in here. So here this by means of this pre-amplifier, that photocurrent is amplified. So what will happen is that it will convert this voltage pulses to adequate voltage levels. Then what will happen is the signal from this output of this front end amplifier that will be given to the filter, or we can call it as equalizer. So here this compensation is made between the input and the reference voltages. So and from this we can able to find out the output signal that will be generated, which controls the gain as well as the pre-amplifier gain. So the noise output is then reduced to the desired level by using this band limiting filter, and or we can call it as equalizer. And then the signal is amplified to the signal data level by using the sample circuit, and finally decision will be taken based upon the amplified signal. So this is about the basic sections of optical receiver, how the signal is, that is optical signal is converted into the electrical signal. So next comes this digital signal transmission. So for example, we'll be considering a digital signal transmission, how this digital signal is transmitted from the transmitter side to the receiver side. So here we'll be considering a two-level binary data stream, which is consisting of either zeros or ones in the time slot. And we'll be taking the time duration as TB, which is nothing but the TB is nothing but it's a duration, and whether this pulse is transmitted or not. So the time slot is referred to as bit period. We can call it as bit period, so that we will be just denoting it as TB. Now this data are transmitted by using this amplitude shift keying techniques. So here this voltage level is switched between two values, either on or off. Now this resultant signal consists of voltage pulses of amplitude V relative to the maximum voltage level for binary 1 and 0 voltage level. Now this optical transmitter converts this electrical signal into there is optical transmitter which converts the electrical signal into optical signal. Now this electrical current I of t that can be used to modulate the light source. So which will produce as the optical output with the power of P of t. And then it is given to the optical signal equivalent for one is pulse of optical power of duration Tb, whereas 0 is nothing but absence of light. So the duration Tb, which represents there is a light, and this duration 0, which represents no light, and that will be given to the other end of the optical fiber. Now this other end of the optical fiber that will be connected to the pin or avalanche photodiode. So again, as usual, what will happen is this optical signal that will be converted into electric current pulses containing photodetector noise. Then that will be given to the amplifier and filter. The output of this amplifier and filters are nothing but voltage pulses, and which will have the amplifier noise. And finally, the signals are given to the decision circuit and pulse regenerator. Finally, the regenerated output voltage pulses are given to the signal processing equipment. So here this arrow marks which denotes the time slots at the center point. So this is about how the digital signals are transmitted from the transmitter side to the receiver. So how this data is, that is signal path through an optical data link, and the signal it may be in digital or it may be in analog, or sometimes it may be in voice signal. So anything that can be transmitted through optical fiber cable. So this is about the operation of digital signal through the optical fiber. So next comes what are the error sources. That is, what are the types of noises which are associated with the receiver circuit. So as we know, the main building block of receiver is nothing but photodetector and amplifier. So obviously there are noise sources which are associated with the photodetector as well as which are associated with the amplifier circuit. So first and foremost, when the photon of energy HV is incident to the photodetector, and there will be in photo detection quantum noise, we can call it as Poisson fluctuations. And within that photo detector, and there will be a dark current noise, or there may be in statistical gain fluctuations, particularly for the avalanche photodiode. And next comes bias resistor, which is connected with the amplifier circuit. So due to these variations in the bias resistor, there will be in chances of noise. That noise is called as thermal noise, which is mainly due to the temperature fluctuations. And finally, the noise which is associated with the amplifier is called as amplifier noise. So what we discussed in your the third unit, the same type of noises or error sources that will be possible in the receiver circuit. So here this noise sources will be just classifying into two types, external sources and internal sources. So this noise sources we can just classify into, it may be due to the external sources or it may be due to the internal sources. Now this circuit diagram which gives the equivalent circuit of an optical receiver for the digital optical communication system. And now in this circuit, and we'll be using that the components are, and basically it has three basic stages. One is photodetector. So here it is a photodetector, next to that an amplifier circuit, and finally equalizer. Okay. So this photodetector, it may be in fin photodiode or it may be an avalanche photodiode. Suppose if it is in fin photodiode, then multiplication factor m is equal to 1. And suppose if it is an avalanche photodiode, then m which will have the values. And next to that, there is an amplifier circuit. As we discussed, this amplifier, which is also called as pre-amplifier. So this amplifier input impedance is parallel combination of resistance Ra and the capacitance Ca. So this amplifying function is represented by the voltage controlled current source, which is characterized by the that is a transconductance Gm. And next to this is nothing but equalizer. So this equalizer, which is also called as a linear frequency shaping filter. So what is the purpose of this equalizer is nothing but it is used to compensate the effect of signal distortion as well as intersymbol interference. That is, it accepts the that is a combined frequency response of transmitter, fiber and receiver, and then it transforms into a single signal response. So that is the purpose of equalizer in the optical receiver circuit. So the purpose of front-end amplifier is nothing but there are noise sources at the front end of the receiver that dominate the sensitivity as well as bandwidth. So front-end amplifiers are used in optical fiber communication system to maximize the receiver sensitivity while maintaining a suitable bandwidth. There are two types of front-end amplifiers. One is high impedance amplifier, the other one is trans-impedance amplifier. So this is a circuit diagram for the high impedance amplifier. In this, using this high impedance amplifier, so the thermal noise is inversely proportional to the load resistance, as we already discussed. So therefore, what will happen is this load resistance RL that should be as large as possible. Only then we can able to minimize the thermal noise. And then and suppose say for example the bandwidth is inversely proportional to the resistance Rp, where Rp is nothing but it's a resistance for the photodiode. So suppose if this Rp is equal to RL for a high impedance front end, then high load resistance results in low noise, but at the same time which will give you the low receiver bandwidth. So these are all the advantages and disadvantages of high impedance amplifier. Next comes trans impedance amplifier. So this is a circuit diagram for the trans-impedance amplifier. So which overcomes the drawbacks of high impedance amplifier what we discussed in your previous slide. Here this load resistance RL is used as a negative feedback resistor around this inverting amplifier. Now this RL that can be that is a large since the negative feedback reduces the effective resistance. So therefore we can write it as the resistance for the photodiode that is equal to RL by G plus 1, where G is nothing but gain of the amplifier, which means that it is compared to the high impedance amplifier design, the trans impedance bandwidth increases by the factor of G plus 1 for the same load of resistance. So therefore the trans impedance front end design tends to be the amplifier of choice for optical fiber transmission link when compared to the high impedance amplifier. So this is about the front end amplifier that will be used in the optical receiver circuit. So thank you for your name.